I didn't.
Okay.
We're basically the same.
Yeah.
System.
So if I do one, then try the other one yourselves afterwards. So, okay, we'll start with 18. So you have, and actually I'll just make this bigger. Okay, so we've got the integral from 0 to k of 2x minus 4 dx. And they're telling us that after we do the subbing, that's going to equal to -3. Because remember, this is a definite integral. And so when you integrate it, do your substitution, your answer should be -3. And they also say the k should be greater than 0. And we'll see why that is in a minute. So if I integrate this, Joe, what am I going to get?
(2x squared over 2 minus 4x).
Good. Okay, and the 2's cancel, so you've just x squared minus 4x, and that's from 0 to k. Okay. So then we do the substituting in. So you sub in your first bracket, you're subbing in k. So you've got k squared minus 4k. So wherever there's an x, you put in a k. Second bracket, you're subbing in 0, which is just going to give you 0 and 0. So that tells you k squared minus 4k. When we work that all out, we know it's equal to -3. So what kind of equation have we got now? Yeah, okay, so you bring the 3 over, get rid of the brackets, you don't really need them, and then you're just factorizing that. K minus 3 and minus 1 equals 0, so k is equal to 3 or 1. So that's all you're doing. So if one of the limits is a letter, you're just going to change x to whatever that letter is. And then you just go ahead with the other information you have. So just like a regular thing, you sub the k in, you sub the 0 in, but you know what the answer is going to be. And that allows you to work backwards to find k. All right, so you should be able to do 19 yourselves now, yeah? The exact same. So try 19 at home, or maybe by the time we get to the end of this class, you might have time to come back to it. And 23 part 1. Any other ones before 23?
No, I understood the rest of them, I think, fairly well.
So we've got 23 is 0 to 2 of e to the 4x dx. And where am I log tables now? So if you have e to the ax, when you integrate it, it's 1 over a e to the ax. So a in this case is 4, so we've got 1 over 4 e to the 4x. Okay. And you can take the 1 over 4 outside the brackets or leave it inside, doesn't really matter. E to the 4x. Actually, let's leave it outside because it's a common factor. And we're subbing in 0 and 2. So that gives you 1 over 4. First bracket is e to the 4 times 2, so that's e to the 8. Second bracket is e to the 4 times 0, which is e to the 0. And what's anything to the power of 0? 1. Okay, so that's your answer. And you can leave it in that form. That's perfectly acceptable. I'm not sure if that's what they have at the back of the book, or did they actually work it out in decimals? It's 3.4. 2.423. Yeah, they just left it like that. Is that okay?
Yep.
And any other ones?
25.
25. Okay, so 25. We're starting with f of x is equal to cos x over sine x. Show that f dash of x. Okay, so this is kind of one of the ones where you're doing backwards. So f dash of x means we would have to differentiate. Okay, and differentiating that, a couple of ways. We could use the quotient rule because it's 1 divided by the other. Or we could say that sine over cos is tan. Okay, so that's 1 over tan x. yeah, which is tan x to the -1. So the reason I'm doing this is just to save me doing the quotient rule, okay? So if I differentiate that, I bring down the power, which is -1, tan x, change the power to -2. So that's the bracket part done. This is going to be chain rule. So the power, the algebra one is, so dealing with this first, bring down the -1 and that becomes -2. And then if I differentiate the tan, I get sec squared x, okay? Everyone with me so far?
Yeah.
Okay, so that's minus sec squared x over tan squared x, because I'm going to bring this below the line, it becomes plus, and then when we're writing it, we just put the 2 after the tan and avoid the brackets, okay? Now sec squared is 1 over cos squared. Again, if you're not sure, you can look at page 9 or 10 in the tables. No, sorry, 13. So 2 ways, sec squared is 1 plus tan squared. We could do that. Or we can say sec is 1 over cos, okay? So I'm going to change them back to sine and cos. So sec is 1 over cos, and tan is sine over cos, so that becomes 1 over tan would be cos over sine, and because it's tan squared, I'm squaring both of those. The cos is cancelled, and you just end up with -1 over sine squared x. So whenever you're trying to simplify something with trigonometric functions, the best thing is to get them all as sines and cosines, and then you can cancel as you need to. Is that okay?
Yeah.
Okay, so that's the first part. So what they're then saying is, and remember our definition of integration is that f of x is equal to the integral of f prime of x dx, okay? So f of x is cos x over sine x is equal to the integral of -1 over sine squared x dx. Okay, so we know f of x, we started with that, we worked out f prime of x. So using that, what they're asking us to do, okay, so from what we've done, we know this. They're asking us to integrate 1 over sine squared x. So if you compare that to that, you can see the only difference is the sign here. So when I do this integration and the limits are pi over 4 to pi over 2. So when I integrate 1 over sine squared, I'm going to get minus cos x divided by sine x. Does everybody understand that?
Yeah.
Yeah.
Because that's your definition of integration. We know what this is, we know what this is. So then going backwards from this, we know we can get this, and that's okay. Because we don't have the integration tools to figure this out using rules of integration. You don't learn that, but so what you can do is, if you know that it's the derivative of something else, you can work it out. And then we're doing that from pi over 4 to pi over 2. So your first bracket is minus cos pi over 2 divided by sine pi over 2. And your second bracket is minus cos pi over 4 divided by sine pi over 4. And cos pi over 2 is 0. So that's just 0 minus 2 minuses is plus. Cos pi over 4 and sine pi over 4 are both 1 over root 2. So that just ends up being 1. And that's your final answer. You'll find with a lot of the trigonometric functions, they end up coming out like from horribly complicated looking things to just the answer being 1 or a half or root 3 or something like that. They simplify quite easily. So the main part of that question was actually differentiating and then the substituting in. So sometimes you kind of need to differentiate in order to be able to integrate, but they would have to kind of tell you that to start with. And to be honest, I've never seen one like that come up in an exam. So I wouldn't worry too much about it. All right, so what I'm going to do, just want to check how many people are actually on. 14 was selected. 13, so missing a few. I record, I'm kind of starting to do a few recordings because then it's available if you want to look back over it, or if people are missing the class, they can check back. So I'm going to record this little teaching part of the lesson, if that's okay with everyone.
Yes.
But if you do want to interrupt with the question, that's fine too. So we're moving on to 3.5, which is page 81 in the book, areas by integration. And this is the main application of integration. So let me just get this set up. So record. Okay, so we're gone live. And section 3.5. Actually, you know what? I'm going to put it up in the camera because it'll just give us a bigger picture. So finding areas by integration, as I said, this is one of the main applications of integration. It's when you integrate, what you're actually doing is finding the area under a curve, so under f of x, between 2 points. And usually it's 2 vertical lines. There is a way to do it horizontally as well if you want to kind of find an area this way, but you don't really have to worry about that. So I'm going to show you why that works, and it's to do with adding up slices of the curve. So if we just have our x and y axes and we have some random curve, y is equal to f of x. And I want to get the area from here to here. Okay, so we'll call it, this is our limits of integration. So starting with A and finishing with B. Now, if I was just taking a guesstimate of the area, what I can do is just divide it into lots of little slices. The kind of, we're going to approximate to being rectangles. Okay, so each of those slices is, we call it h wide. So we're starting, each of those slices is h, okay? So they're all the same width. And the first, we'll call the first point x equal to a. So then you've got x plus h, x plus 2h, x plus 3h, all the way up to b, okay? And we're starting with, finishing with x equal to b. Now, to guess the area of each of these, we're going to assume that they're little rectangles. So I'm just going to draw a line across the curve going from one point to the other. So we're kind of making rectangles here. See that? And we know the area of a rectangle is length by width. So they all have the same, so area of a rectangle is length by width. Okay, width in all of these is that little distance h. Okay, so they're all the identical width h. Their height, so the height is where they're hitting the graph, which is basically at every point, it's f of x at that point. Okay, so if you're at this point here, whatever x is, this height of this rectangle is f of x, f of x, f of x. So as x changes, f of x is changing. Does that make sense to everybody?
Yeah.
Okay, so if we want to get the area, what we're doing is we're adding up. Remember this sign for adding? Okay, the sigma sign, we use that in, have you all seen that before?
Yep.
Yeah.
Yep.
So we're adding up all of those f of x's times, so that's the length by the width, okay? And we're starting at x equal to a, and we're going to finish at x equal to b. And if you like, when you look at h, it's basically the change in x. So h is actually equal to what we could call delta x, or the change in x. So we've got the sum of f of x times delta x starting to a and finishing at b. And that'll give us a rough, it's obviously going to be an overestimate. And if your curve was kind of like this, all your rectangles would be under the curve, so it'd be an underestimate. But it's an estimate. Does that make sense of the area? So what we want to do is to get it more accurate, if you make those H's, the delta X is very, very small, then you're going to get much thinner slices, and your f of x is going to be the exact value of the height of each of those very thin rectangles. So we're getting the limit as, if you like, delta x, or h tends to 0, of the sum of f of x delta x. And as delta x turns to 0, what we do is, instead of saying we have all those little slices added up separately, integrating them means smoothing it all together. So we change our sigma sign here into our integration sign. So integration literally means the sum of all those slices, but it's a continuous rather than, these are what we call, this is discrete, which means you can separate all the slices. But when we integrate, we've made the delta x so small that it becomes continuous. And that's for f of x, I'm sorry, we still have our a to b, dx from a to b, and that's equal to the area. Okay, so that's your definition of finding the area under a curve, is if you integrate it, your limits are where you start the area and finish the area, and it's the integral of the actual curve times dx. So the big thing here is integration is equal to area under a curve. All right, so just like we know differentiation is getting the slope, or it's getting the rate of change. If we want to use integration, we use it to find the area under a curve. And when I say under, I mean between the curve and the x-axis. And your curve is f of x and the x-axis, and also between the two vertical lines, x equal to a and x equal to b. So it's enclosed in those four functions, if you like. First one is f of x, second one is the x-axis, and then you're going from a to b. So that encloses an area, and if we want to find the area, we integrate. So I'm going to stop recording now before we do, because I don't want it to be too long. All right, and I'll upload that to Drive, so that's available if anybody wants to go back over it. So if you want to turn over the page, there's our definition. So this is the key takeaway from this, is that the area of the region between the curve f of x and the x-axis between the two lines is the integral from a to b of f of x dx. Okay. One thing to be aware of is if the curve crosses the x-axis, because f of x is minus here, if you integrate this, you get minus. Okay. So if we're integrating, say this is a to b, if you were to integrate from a to b, some of this would cancel out some of this, and you'd end up getting 0, which obviously isn't the area. So what you need to do is put in an intermediate point. If your curve crosses the axis, you want to go from here to here, ignore the signs, because remember, areas should always be positive. All right, so you're going to integrate to where it crosses the x-axis, and then you're going to integrate this bit, but you're going to ignore the sign. You're going to make sure it's positive, and then you're going to add those two pieces together. That makes sense? So you take the absolute value to be the area, okay? So the key, when you're asked, like some of the questions might just give you a diagram and say, find the area. First thing you need to figure out is, where am I integrating? Where am I starting and where am I finishing? And sometimes you might have to divide it into 2 or 3 segments, depending on whether it's going up above or below the axis, because you want them all to be positive. So just be aware of that. the other thing is, as I mentioned, and this doesn't really come up very often, but just to know, you can also get the area between the curve and the y-axis. And what you have to do here is use inverse functions. So instead of y being f of x, we'd have to rearrange it. So if you had something like y is equal to x squared, say, okay, you need to change that to x is equal to square root of y. So now x is a function of y, okay? So x is equal to f of y. And then you would integrate this one with respect to y. Okay, so you're just changing your variables. And what you're doing when you do that is instead of going under the curve this way to the x-axis, you're going across this way to the y-axis. So if you're ever asked to get area between a curve and the y-axis, you need to get the inverse of the function. You need to rearrange the function and then integrate with respect to y. Is that clear enough for everyone?
Yeah.
Okay. And again, you'd have to make sure, you know, if they're saying between 0 and 4, you say, oh, hang on, across is here at 2. So I need to go from 0 to 2, and then I need to go from 2 to 4 separately. And then when I've got those two answers, I add them both together to make sure that they're not cancelling each other out. Okay, so let's look at example 1. And I'm going to record this one as well. This recording's a little bit stressful, but hopefully it's helpful for people. Okay, so example 1, the area of the shaded region shown in the diagram. So if you were given this in a test, you'd be just given, find the area enclosed between x squared minus 4 and the lines x equal to 1 and x equal to 4. And you might be inclined to just go integral from 1 to 4 of x squared minus 4 dx. That's not going to give you the right answer because some of that integral would be negative. So if you just went from 1 to 4, this part would cancel out this part, which you don't want. When you're getting area, you have to make sure it's all positive. So we have to split it up into from 1 to 2, because that's where it first crosses. So we're starting at 1, and we're going to have the same sign until we get to 2. So we can go from 1 to 2 of x squared minus 4 dx. And then we're going to add the integral from 2 to 4. So this one, the top of this one, your upper limit here becomes your lower limit here. And you want to make sure you take the absolute value of both of those. So when we integrate this, we get x cubed over 3 minus 4x. And we put in our limits 1 to 2. And then this one, the exact same integral. And the limits are 2 to 4. So you're going to have your two brackets here for your two subbing in. So you sub in 2, you get 2 cubed over 3 minus 4 times 2. That's your first bracket, minus 1 cubed over 3 minus 4 times 1. So that's all of that part done. And then separately you do this part. So you've got 4 cubed over 3 minus 4 times 4. That's subbing in the 4. First bracket for that integration. And the second bracket is 2 cubed over 3 minus 4 times 2. And you can work out each of those separately. So we have 2 cubed over 3 is, so just grab the calculator. I know it's done in the book, but just to show how it works. So you've got 2 cubed over 3 minus 4 times 2. That's negative 16 over 3. Now, we're not ignoring the minus here because we're still working out the value of this integral. The second bracket here is 1 cubed, which is just 1 over 3 minus 4. That's minus negative 11 over 3. So you have negative 16 over 3 minus negative 11 over 3, which is our previous answer, which gives you, sorry, I have got the minus there. Negative 16 over 3 minus negative 11 over 3 is minus 5 over 3. And this is the integral of this, so we're going to ignore the minus there. So that is 5 over 3. And on this section here, then we have 4 cubed is 64 over 3 minus 4 fours is 16. So 64 over 3 minus 16 is 16 over 3 minus, and we know this one, we already worked it out here, is negative 16 over 3. And the 2 minus there will cancel. So you have 16 over 3 times 2. That's 32 over 3. And that is positive, so we don't have to worry about changing the sign. And then you add the two of them together and you get 37 over 3. And that's your final answer. So any questions on that? You okay with that?
Yep.
Yeah.
Yep.
Yeah.
So before we go on to area between two curves, we'll just do a couple of examples on that. So if you go to 3.5 on page 85, let's do the camera seems to have frozen. Okay, let's do it out of the book. So we're going to do question 2, question 4, so 2, 4, 5, 7. And see the way 7 has 3 different parts?
Yes.
Everybody see that?
Do you have to use?
Sorry?
Do you do it then 3 times?
Yeah, so you go -1 to 0, 0 to 3, and then 3 to 4.
Okay.
Now you'll end up getting from -1 to 0, you can kind of see the symmetry there. They should both be the same. So you can kind of cheat a bit and just put in the same number here. That makes sense. And then add it to this one.
Oh, okay.
Yeah. So
Yeah, I
2,
gotcha.
5, and 7. And let's do 10 as well, just to get an example of when you're doing it in Y. So 2, 4, 5, 7, 10. I'll put that up in Classroom now. Take the roll now, lads. So Andre, yeah, Matthew, Sean. Aaron. Aaron there at all? Beth, was he around?
Sorry, I don't actually. I'm not sure.
Okay, all right, I'm marking it. Accordion, is here. Andrew. Ben, Jamie, Pavel, Dylan, Andre, and yeah. Check your answers as you go along, make sure you're doing it properly. Shout if you're getting stuck on anything. Everybody doing okay?
Yeah.
Yep.
Okay, I'll let you go. So, and see you tomorrow morning.
Thanks, Miss.
Thank you.
Thank you.
All right, lads.
Thank you.
Thanks, miss.
Thank you.
Take care.